Combined Science, Physics, Higher Tier, Paper 1, Walkthrough. Wind power and solar power are both renewable energy resources used to generate electricity for the national grid. Which of the following is also a renewable resource? What does renewable energy resource mean? It means that after it's used, it's replenished, or there's lots of it that it can never be used up. Geothermal is renewable. Natural gas is not, because it's a fossil fuel and it forms under the sea or under the rocks, and that can't be replaced as fast as it's being used. Nuclear fuel, elements such as uranium, once we've used it up, we don't have anymore. It's a finite resource. The energy transferred by the national grid in 1 second was 36 gigajoules. Giga. Which of the following is the same as 36 gigajoules? Well, we have to remind ourselves what giga means. We start with the unit, and then going up we have kilo, then mega, then giga. Each time we go up in multiples of 3. Kilo is times 10 to the 3, mega is times 10 to the 6, giga is therefore times 10 to the 9. So 36 times 10 to the 9 joules equals 36 gigajoules. Figure 1 shows how the mean power output from the solar and wind energy resources in the UK varied between 2014 and 2019. Figure 2 shows how the power output from the solar and wind energy resources varies in a typical year. Explain the changes in the power output from the solar and wind energy resources between 2014 and 2019. You should include an explanation for the change in the power output during a typical year. I'll tell you now, if they've given you 2 graphs, to get the 6 marks, you need to talk about both graphs. And remember, an explain question, I'm going to highlight the word explain, requires you to say, write a detailed answer that covers how and why something happens, and give reasons. When you give reasons, you use the words because, so, therefore, right? So you say a statement and then use one of these words and then say your reason. This is the typical makeup of a explain question. So every point that you're going to make, you're going to say a statement, because, reason. Now let's have a look at the graphs in a little bit of detail, and then we're going to go on to answer it. Mean power output in megawatts means how much power is outputted each year, an average of it in megawatts. So where it says 1,000, 2,000, 3,000, they're talking about 1,000 megawatts, 2,000 megawatts. The solar power is given as a grey bar, and the wind power is given as a lighter grey bar. Now you have to understand that the solar power is much less than wind power, and you have to think about why that is. Remember, we're talking about the UK here. Figure 2 shows the power output from the solar and wind energy resources varies in a typical year. Again, power output in megawatts, it's not the mean because it can give how much it is each month. So it goes from January to December, and the trend is for the wind that it goes down towards July and then back up again. For the trend for solar is that it goes up from January to July and then back down again. Solar power is given as a dotted line, wind power is given as a solid line. Once we've got that, we're ready to answer the question. Part 1. Let's talk about the figure 1 first, and we'll use bullet points, and we'll write the word because in between each of the statement and the reason. So the first statement I'm going to make is the fact that from 2014 to 2019, the wind power, the trend in wind power has increased. And I'm going to use the word mean power output. Of wind increased. And remember, the word that I'm using is because, and I'm going to write my reason. Well, why will they have increased? The UK will have invested more money in renewable energy resources, so they'll put more wind turbines up. So more wind turbines, more wind power. Turbines. Okay, next question, next statement. Well, what happens to the solar energy? It also increases, not as much as the wind, but it also increases. So if you want more solar energy, more power output. Sorry, mean power output. Power output of solar increased, and the because has to be because more solar panels built. Now, there's a statement to be made there that the change in wind and solar could be related to climate change. If it became significantly more windy from 2014 to 2019, that could have caused more wind power output. And if it became significantly more sunny from 2014 to 2019, that could have caused more solar power output. So we could make that statement that, although that is kind of separate to your explanation, the increase in power output may be due to climate change. And there's another thing that we could make a comment about, and I'm going to do it in a different color still, is that at this point it seems that the wind power decreased for 1 year, for 2015 to 2016. Why did wind power decrease? Because wind power decreased because remember, that's the key word, less windy. 2016. I mean, those are statements that we're sort of making, and we're not fully sure about the less windy bit, but these first two statements we are very, very sure about. Then figure 2. Okay, continuing with your same answer. In figure 2, you have from January to July, the wind power output decreased. From July to December, it increased again. So why did the wind power output decrease in July? Less wind power output in July because remember, summer months are less windy. In the same way, more solar power output in July, May, June, July, I should say. May to July, as it is more sunny. Okay, as it is because it is more sunny. Okay, other statements that we could make. No, I suppose we couldn't say more sunny because there is more sunlight hours. hours in the summer months. Other statements that we can make are for most of the year, most of the year, wind power generated is greater because the UK is windier. All of those statements you could make. Next. Body analysis skills use the electrical resistance of a person's legs to estimate the percentage of water in a person's body. The person's legs contain both solid tissue and water. A student used resistors to model the solid tissue and water. The student connected a 20 ohm resistor in parallel with the resistor R. Figure 4 shows the circuit diagram. To determine the total resistance of both resistors, a voltmeter must be connected into the circuit. Complete figure 4, show where the voltmeter should be connected, and it needs to show the total resistance of both resistors. Remember, this is a symbol for a voltmeter, and it can be placed right here where it is across both resistors, or right here where it's also across both resistors. The student calculated the total resistance of the two resistors. The student's answer was 26 ohms. Explain why the student's answer cannot be correct. Let's remind ourselves of what that setup looks like. Here's a 20 ohm resistor and the resistor R. The student is trying to say that this two resistors added together will make 26 ohms. But this can't be correct. Student's answer must be less than 20. Now why? Because, remember it's an explain question, because the total resistance of resistors in parallel must be less than the resistance of the smallest resistor. Okay, let's imagine why that is. The total resistance of the resistors in parallel must be less than the resistance of the smallest resistor. Now, if the 20 ohm resistor was the smallest of the two resistors, then it has to be less than 20. If R is smaller than the 20 ohm resistor, it's still, the total resistance has to be less than 20. This is because when you add resistors or any branches in parallel, you are adding another pathway for the electrons to flow. More pathways for the electrons to flow means the rate of flow of charge, current, is higher. If the current is higher, you're imagining, oh, if the current is higher, that means there must be less resistance. When you're adding more pathways, you're decreasing the total resistance. Use the physics equation sheet to answer questions 2.3 and 2.4. Write down the equation that links current, resistance, and potential difference. This is V is equal to I times R, or potential difference is equal to current times by resistance. While we're here, just remind ourselves of what the units are. Potential difference is measured in volts, current is measured in amps, and resistance is measured in ohms. That might be useful next. When the total resistance of the resistor was 7.5 ohms, the current in the circuit was 480 milliamps. Calculate the potential difference across the two resistors. I'll say it again. When the total resistance of the resistors was 7.5 ohms, the current in the circuit was 480 milliamps. calculate the potential difference across the two resistors. Now the resistance is in the correct units, but the current happens to be in milliamps. Let's go back to the conversion. Units, and if it gets bigger it becomes kilo or mega or giga, but as it gets smaller it's milli, and then micro, nano. Now we're only caring about the milli, which is units times 10 to the minus 3, otherwise divide by 1,000. So the first thing we need to do is do a conversion. 480 milliamps is equal to, and when we divide by 1,000, 0.48 amps. Okay, so that was my current. I'll put an I next to that. Next, calculate the potential difference. So to calculate the potential difference, we need the equation V equals I times R. I know my I, which is 0.48 times by my R is 7.5. 0.48 times by 7.5 gets you an answer of 3.6 volts. Superb. The student investigated how the resistance of R affected the total resistance of the circuit. I'm reading from here, by the way. Table 1 shows the result. Resistance of R in ohms is on the left hand side of the table, and the total resistance of the circuit in ohms is on the right hand side of the table, and it gives all values. Some of the results are plotted in figure 5, which is right here, and it asks, and moving on to here by the way, it asks complete figure 5. I've chopped it up so it all fits on one page. You should label both axes, plot the two remaining values from table 1 and draw the line of best fit. It gives you 3 marks and it tells you exactly where to collect those marks from. So let's start. Label both axes. The axes are labeled. This will be on the x-axis and this will be on the y-axis. So the x-axis should read resistance of R in ohms. Resistance of R in ohms. And it's good practice to underline your axis title. The y-axis should read the total resistance of the circuit in ohms. Total resistance of the circuit in ohms. Be neater than I am being right here because my handwriting on this tablet isn't as neat as it ought to be. So we can tick that off. We've done that. Plot the two remaining values from table 1. Let's see which values have been plotted. 5 equating a total resistance of 4 ohms, that has been plotted. 10 has been plotted. 15 has not been plotted, which we need to, so I'm going to put a circle there so I can tick it and edit. And 20 hasn't been plotted, but 25 has been plotted. 15 ohms of resistance of R gives 8.6 ohms of resistance of the total circuit. So let's see what each tiny square goes up in for the y-axis, because I know I can start at 15 but I don't know how far I need to go up the y-axis. Each tiny square, well, there seems to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tiny squares in between 0 and 2. Therefore, each tiny square is 0.2. When we get to 8, I need to count up to 8.6, and I know for each small square I'm counting in 0.2s. So 8.2, 8.4, 8.6. And then I just put a X, exactly like how the plots are for the rest of them. So I'm going to just make sure that the X crosses, and it's only a small cross, and it can't be bigger than the small squares. So it can't be any bigger than how big I've done it. All right, and I've done it a little bit bigger so that you can see it. We've done one. Now let's do the next one. For 20 ohms, it's 10 ohms of total resistance. 20, 10, and that's easy value. Notice I'm struggling because on the tablet it's very difficult to get it precise. So we've plotted the two remaining points. Now we have to draw a line of best fit. Now if this was an easy line of best fit, which was a straight line, I could do something like that. And you can tell, even when I'm drawing it, I'm tempted to curve it because I can see the plots curving. So if it is a curved line of best fit, go with your gut and plot the curved line of best fit. And it seems it is a curved line of best fit. I'm going to re-jiggle that again because I haven't done it properly. There you go. I've done as many points as I can, but without taking my hand off the page, and it's a curved line. Next question. What resistance of R would give a total resistance of 4.4 ohms? Now, if you've drawn your line of best fit correctly, you go to a total resistance of 4.4 ohms, and then you work down. So 4.4 happens to be 4.1, 4.2, 4.3, 4.4. Sorry, 4.2, 4.4, which happens to be right there. And then I look down, and that resistance of R will give a total resistance of 4.4 ohms. Obviously, all of this has to be done using a pencil and a ruler. And then I can count what that is. Each tiny square goes up in 1. So the resistance of 7 ohms would give a total resistance of 4.4 ohms. Superb. So the body analysis scales initially show a reading of 0.0 kilograms. When the student steps onto the scales, the reading is 64.8 kilograms. The student steps off the scales and then immediately steps back on the scales and now show a reading of 64.1 kilogram. Complete the sentence. The difference between the two values given by the scales is due to a something error. Now, there are three types of errors that you need to know about. There are zero errors, systematic, and random. Zero errors are common when you're measuring something from a scale, weighing things. If the scale already reads 0.1 or 0.3 or minus 0.1 or 0. I don't know. If it's not on 0, then when you take a measurement, you'll get a 0 error. But it is on 0, so it's not a 0 error. A systematic error is when you measure something over and over again, but your measuring equipment has been measured from the wrong point, or you're looking at it from a different level, but you're looking at it from the same level each time. So the error is off, the correct value is off by the same amount for each of the repeats. Well, we don't know that, so we're going to assume it's not a systematic error. But a random error is a human error in measuring, or just something that you can't explain. So for this case, it's a random error. The height of the student is programmed into the scales. The scales place the student into a category, A, B, or C, based on their height and mass. Figure 6 shows how the scales use the category and the total resistance of the legs to determine the body water percentage. So on figure 6, you can see that the y-axis shows the body water percentage, whereas the x-axis shows the total resistance in the legs in kilo ohms. A, B, and C are lines that show which category anyone could be in. The total resistance of the student's legs is 600 kilo ohms, and a healthy body water percentage is between 45 and 65. The different measurements of the mass of the student mean that the student could either be in category A or category B. Remember, the different measurements comes from the earlier question. But we don't have to associate the measurements with the category, because the question is Evaluate if the student has a healthy body water percentage. And evaluate typically means you'll be given some facts or information and you have to write about the data that you're given and write a conclusion about them. In this case, the conclusion is the student's body water percentage healthy? To do that, first we identify which is the healthy body water percentage, and it's 45 to 65%. Now, because I'm having to draw on this tablet, I've animated some of the things that I would normally draw on. So I would first draw from 45 to 65, and I would draw lines to show this is the healthy body water percentage. That tells me, or this bar where you can see it's shaded in green, tells me if the value lies in between those 2 points, it's a healthy body water percentage. Next, we need to know what the student's measurement was. It tells us that the student's measurement is 600 kiloohms. So that's what I'll draw next. Again, I've used animations. Looking at the red line, I can see that the red line meets the category A, B, and C values at the points shown. And these blue dots show the points where A and B are meeting the red line. I haven't bothered with C because we know the student isn't in category C. Now we see that if the student is in category A, they lie within the green box. If the student is in category B, they lie outside of the green box. We have to first determine what their body water percentage is. In category A, it seems to be around 61, and if they were in category B, it seems to be around 68. Reading these values off, I can start answering my question. In category A, I'm going to put cat for that, category A, body water percentage equals 61%. In category B, body water percentage equals 68%. Now we can say what our conclusion is. We've stated the facts, we've worked it out using the graph. Our conclusion is, and I'm going to do it in a different color, if student was in category A, they have a healthy body water percentage if the student was in category B, they do not have healthy body water percentage. The hardest thing for me in this question is writing body water percentage out, and obviously writing category out. I've been really lazy here and I've contracted category to cat, but obviously that's unacceptable. So just to recap, where the student's line intersects, which means crosses the lines of the category, we read off that point to the y-axis to see how much body water percentage that particular reading of resistance will show for each category. Now, there are points on the graph where all three categories can be sort of seen in one. I think somewhere around here, or maybe I've had to No, there's never actually a point where both all three categories can be healthy. But say for example, your reading was 800 kiloohms. Because it doesn't intersect with A, you can't be in category A. But if you're in B or C, you are healthy. Next. Figure 7 shows how the national grid transfers energy from a power station to some street lamps. Explain how the transformer X increases the efficiency of the national grid. Let's label the national grid. From the power station, it goes into the first transformer, which is called a step up transformer, and then goes into the transmission cables, which are on pylons, and then goes into this next transformer, which is the step down transformer. Then it goes into street lamps or houses or companies. Explain how transformer X increases the efficiency. Well, increasing efficiency means decreasing wasted energy. So how does transformer X help less energy be wasted? The first thing that the transformer X does is increases potential difference. Because that is the job of the step-up transformer. It increases potential difference. More potential difference in the cables means less current. So what it does is decreases current. If potential difference increases and current decreases, and remember, current contributes to heating up the wire, less energy is going to be wasted in heating the transmission cables. If less energy is wasted, it means it's more efficient. The potential difference across the primary coil and the transformer is 400,000 volts, and the potential difference across the secondary coil is 11,000 volts. The current in the primary coil is 660 amps, and the current in the secondary coil of the transformer is calculate the current in the secondary coil of the transformer Y. Use the physics equation sheet. Now we know that Y is a step down transformer. We know that 400,000 volts is Vp, and this is Vs, and this is Ip, and what we're trying to find is Is. The equation is Vp times by Ip is equal to Vs times by Is. Now where does this equation come from? You can find this equation in the equation sheet, but this equation comes from the fact that power is equal to voltage times by current. Even when there is a step up and a step down in this transformer, the power in the cables remains the same, right? The power remains the same. So the power in the transmission lines is equal to the power after the transformer. So what we have to now do is put the numbers that we have in. Vp is obviously equal to 400,000. So 400,000 times by 660 amps for the current is equal to 11,000 times by Is, which we're trying to find. Now, all we do is Is, rearrange the equation to make Is the subject, the current the subject, is equal to 400,000 times by 660, all divided by 11,000. Okay. So I just have to plug this into the calculator. And when I do, it ends up being 24,000 amps. Okay, easy. Why is the current in each each street lamp less than the current in the secondary coil in transformer Y? Well, the current splits up as it goes to each of those lamps because the lamps are connected in parallel. Figure 8 shows the top of the street lamp. The light sensor detects if it's day or night, and figure 9 shows part of the circuit in the light sensor. So in figure 9 there is the LDR, and this is the resistor that they're talking about, resistor R, because it says explain what happens to the potential difference, the voltage, there you go, across the resistor R when the light intensity decreases. So light intensity decreasing for an LDR, this is the graph that should come to mind. When the light intensity increases, the resistance decreases. So when the light intensity decreases, the resistance increases. When it's dark, the resistance of the LDR is high. If the resistance of the LDR is high, then the potential difference across the LDR is also high. That's what's given. And that means the LDR takes a greater proportion of the potential difference from the battery than the resistor R, which means the resistor R will have less potential difference. Or another way to think about it is, if the resistance from the LDR is high, then the current through the circuit is low. If the current through the circuit is low, then for the same resistance you have less potential difference. For R, that means R will have less potential difference. I'm going to write both versions of the answer. Okay, but it both starts off by saying resistance of the LDR increases. So in one way you can say current decreases, or you could say the LDR has a greater share of the potential difference. Of potential difference. The next thing that you could say, or that you have to say, is the potential difference across the R decreases. R decreases. Okay, so notice the two routes that I have taken for a 3-mark question. When the current in the resistor R is 20 milliamps, the power transferred by the resistor R is 6 watts. Calculate the resistance of the resistor R. I'm just going to remind myself of all the things that I have. When the current is that, the power is that, it asks for resistance. The equation that links P, I, and R is power is equal to I squared R. Okay, now we can write down what the terms that we have are. Current is equal to 20 milliamps. Immediately I recognize that I need it in amps, so I convert that to amps. 20 milliamps is converted into amps by dividing it by 1000. So it's converted into 0.02 amps. That's my current. My resistance is what I'm trying to calculate. and power is 6. Then I do my substitution. 6 is equal to, power is equal to 0.02 squared times by resistance of R. Next, I rearrange. R is equal to 6 divided by 0.02 squared. Finally, I write down what the answer is, which is 15,000 ohms. Okay, the other way of doing this is, of course, by using V equals IR and then calculating potential difference, then using power equals I times V. That will get you, by using power equals I times by V, calculating what V is, then using V equals IR to find what resistance is. Okay. Question 4. A scientist investigated a sample of radioactive material to determine if it would be suitable for medical use. The method, results, and conclusions of the scientist will need to be checked by other scientists before the results of the investigation are published. What is the name given to the checking process where other scientists check one scientist's work? All these scientists are peers and they're reviewing each other's work, so it's called peer review. There is an increased risk of cancer if the scientist is irradiated by nuclear radiation. What property of nuclear radiation causes an increased risk of cancer? Cancer is caused by the radiation knocking electrons off atoms, which means they can disrupt the atoms inside the DNA, which could cause cancer. That property is called ionization. Something that is highly ionizing is more likely to knock the electrons off the atoms. Next. The activity of a radioactive source is the rate at which the nuclei of the source decay. What is the unit of the activity of the radioactive source? The activity is measured in becquerels. And I would be lying if I told you I remember exactly how to spell it. But it's BECQ, then UEREL, becquerel. But guess what? We can write BQ, which is the symbol of the unit, and we'll get away with it. The scientist placed a radiation detector near the sample and measured the count rate. Explain why the count rate is less than the activity of the sample. In fact, what they're asking you to explain is what is the difference between activity and count rate. So an activity of a substance is all of the radiation emitted by it, and it's emitted in every direction. So here is your radioactive rock, and it's emitting radiation in every direction. Here is your Geiger-Müller tube, and it's only measuring the radiation that goes through the Geiger-Müller tube. You can see that the Geiger-Müller tube is actually only looking at the radiation that it can see. So that's the count rate. The activity is the overall activity. So here's what you write. Not all the radiation emitted is detected Because, remember, it's an explain question, because the radiation spreads out. Now, there are other reasons why. From the source to the detector, there's lots of radiation coming off it, but a lot of it is absorbed by the air. So anything that's absorbed is also not detected. You can just say some radiation is not detected because either it goes in a different direction or it's absorbed. The scientists recorded the count rate from the sample with the radiation detector at different distances from the sample. Table 2 shows the results. The distance between the sample and the detector in centimeters, and then count rate in counts per second. You can see that at 10 centimeters it goes down to 0, and at 5 centimeters it is significantly decreased from the 300 that is at 2 centimeters. Just a 3 centimeter difference, and it's significantly decreased. And after 5 centimeters it's not detected. So we say this is emitted by an, this is alpha radiation, because it's an explain question, so you use the word because the radiation cannot travel 10 centimeters in air. If this was beta, beta can travel meters. It would be detected. If this was gamma, gamma can travel kilometers, so it would be detected. So it has to have been alpha. The scientists moved the detector closer to the sample and started a stopwatch. The scientists measured the count rate from the sample at different times. Table 3 shows some of the results. The scientists realized that 30 minutes, at this point, it was whole number of half-lives. Calculate the value of x in the table 3. That's really interesting. So 30 minutes is a whole number of half-lives. So double the 30 minutes will be double the whole number of half-lives that we've talked about. So the half-lives that it travels through between 1568 and 98 should tell us how much each half-life is. And that should be able to help us calculate what the count rate at x. I'll show you what I mean. So it starts off at 1568. Then one half-life later, it becomes, I'm going to go through different colors because I can. One half-life later, it becomes 1568 divided by 2 becomes 784. Then another half-life later, it becomes 392. And then another half-life later, it becomes 196. And another half-life later, it becomes 98. Oops, forgot to use a different color. 98. Okay, so that many half-lives pass. 1, 2, 3, 4 half-lives later. So 4 half-lives later, it's 98, and 4 half-lives is 60 minutes. So each half-life must be 15 minutes. So therefore, 2 half-lives equals 30 minutes. See where I'm going with this. So 2 half-lives later, it's 30 minutes, and 2 half-lives later, it's 392. And I found my answer. Now, all of the working out that I've done on my right can be put into this little section, and you can get 3 marks. This is the crucial bit. 30 minutes is 2 half-lives. That will get you 1 mark itself. The scientists had a second sample of the radioactive material. The scientists made appropriate measurements, then calculated the half-life of each sample. Why was the half-life calculated from the second sample slightly different from the half-life calculated from the first sample? Why was the half-life calculated from the second sample slightly different? Well, radioactive decay is a random process, so it's not going to be perfect. So that's what we've got. The count rate from the radioactive sample is predictable. No, it isn't. It's random, so it's unpredictable. The samples that are at different temperatures shouldn't affect it because it's happening inside the nucleus, which isn't affected by the temperature. The size of each sample is different. Still shouldn't affect it because if it goes from 1000 to 500 or 500 to 250, it's still the same half-life, isn't it? Oops. Next. Figure 10 shows a child's toy. A child pushes down the toy to compress the spring. The spring then launches the toy into the air, and I can imagine it just goes like that. The student measured the maximum height reached by the toy. The student placed a vertical meter ruler near the toy, observed the height reached by the toy. The student repeated the experiment, observing from a different position. The student repeated the figure 11 shows the toy at its maximum height and the 2 positions the student takes. You're probably asked to comment on which one's better, but let's have a look. Observing the toy from position B instead of position A affected the measurement of the maximum height reached by the toy. Explain how. Okay, have a look. Here is from position A. Let's imagine he's looking at the bottom of the toy because that's the flat bit that he can look at. If he's looking from here, he's sort of seeing that the flat bit has reached over there. I'm exaggerating my lines a little bit. But if he's looking at it dead on, then that's what the case is. You can see in both scenarios, the toy has only reached the same height. This is the blue height is the actual height that the toy has reached. But if he's looking at it from the bottom, it looks like it's reached a higher position. Therefore, position B is more accurate. Position B will be more accurate. Explain. Because the eye is level with the maximum height of the toy at position B. Of the toy at position B. Awesome. That's it. Whereas here, what's this error called? It's called a parallax error. The greatest height reached by the toy was 64 centimeters. I can see a calculation question coming. The gravitational potential energy of the toy was that much, EP. The gravitational field strength is that much. Calculate the mass of the toy. Okay, so we're being given gravitational potential energy, we're being given height, we're asked to calculate mass. M. Let's write down all of the things that we need. EP is equal to 0.049 joules, makes sense. Mass, we don't know, which we're trying to calculate. Gravity is 9.8 newtons per kilograms. And height is 64 centimeters. That doesn't look right. It needs to be in meters. So 64 centimeters is equal to what in meters? 1 centimeter is equal to 0.01 meter, or 100 centimeter is equal to 1 meter. Dividing by 100 is what we have to do. divide by 100, and the answer is 0.64 meters. Now we can do our calculation, but we first need to look at our equation sheet, or from memory of course, give that EP is equal to mgh, or gravitational potential energy is equal to mass times gravity times height. So 0.049 is equal to mass times by 9.8 times by 0.64. Rearrange to make m the subject. Mass is equal to 0.049 divided by 9.8 times by 0.64. If you don't know what I did there, I realized that 9.8 and 6.4 is timesing onto the into the mass. So to get rid of it from this side, I divide this side, but I also have to divide the left hand side and the right hand side by the same thing. So I end up cancelling out 9.8 and 6.4 from the side that m is on, and because I divide m by both of those things, I end up dividing the 0.049 by both of those things. It's simple rearranging. Next, I have to put it into my calculator to find what the answer is, and the answer turns out to be, this is the wrong answer by the way, is 0.0078125 kilograms. But that's unacceptable because I need it to 2 sig figs, and the first significant figure that I see is 7, and the second significant figure that I see is 8, and then afterwards it's not a number bigger than 5, so I don't have to round up, I can round down, and therefore the answer is 0.0078. When the spring launches the toy into the air, the temperature of the air increases. Explain why the child's toy is not a closed system. See, in a closed system, all of the energies can be accounted for, but in this case, energy is dissipated to the surroundings, obviously, or air. Therefore, but I'm going to use, but in a closed system, the total energy remains constant or the same. So if this was happening inside a box where all of the gases energy is accounted for, and then the spring toy was bouncing up into the air, and we can calculate or we can measure how much energy is lost and possibly calculate how much energy is gained by the air, then the whole thing would be a closed system, but not the spring toy on its own. Figure 12 shows a device that uses a mug of hot coffee to turn a wheel. The hot coffee increases the temperature of the air in the chamber. Explain how the pressure in the chamber changes. This is an interesting system. When the pressure in the chamber changes, it pushes, the air obviously pushes apart, which causes the piston to move up, which causes the wheel to turn. But because the pressure increases, the volume increases, the pressure decreases again, which causes the volume to decrease again, and it goes up and down and up and down, and obviously it uses some sort of mechanical linkage to make sure that wheel turns constantly. So explain how the pressure in the chamber changes. Here I'm drawing the chamber out, and there are particles of gas in the chamber, and the heat is being supplied from the bottom. And when the particles of gas have been heated up, they gain, or the particles gain, kinetic energy, which means they move faster faster. And because they move faster, they collide more with the walls of the container. So that's the second marking point. More collisions with the walls of the chamber, or more frequent collisions with the walls of the chamber, which means more pressure. That's it. Next. For the device to work, the air in the chamber must increase in temperature quickly. So here's the chamber. The air must increase quickly in temperature. Explain why the bottom of the air chamber is made of metal rather than plastic. Why is this bit metal rather than plastic? Well, if it was plastic, it would have a poor thermal conductivity. And a poor thermal conductivity will result in a slow energy transfer. We want the energy transfer to be quick. The energy transfer must be fast, or at a greater rate. So, therefore, the material needs to be of a good thermal, or the material needs to be a good thermal conductor. Metals are good thermal conductors. Okay, the mass of the air in the chamber is constant. What property of air allows a small change in the thermal energy to cause a large temperature change to the air in the chamber? What property allows large temperature change when there is a small change in energy? That property, specific heat capacity. Specific heat capacity, remember, is the energy needed to change the temperature of a kilogram of substance by 1 degree. Okay, so if there's less energy needed, that means it's a lower specific heat capacity. Next, the changes in the pressure in the air in the chamber causes the wheel to turn. Okay, so just one way to increase the speed at which the wheel turns. That's a good question. How could I change? I can't change the temperature of the coffee, can I? I could. If there was a hotter coffee, the temperature change would be greater, quicker, which means the pressure would increase, and then it would turn, and then the pressure would release, and then it would turn faster. Yeah, so hotter coffee. What else could I do? I could make sure the wheels parts are lubricated. Parts are lubricated. Put oil on them. And why does the pressure change when it gets to the top? Because of the temperature of the air. So cooler room. So those three things can affect how fast the wheel. The temperature of the coffee decreases as the device is used. The initial temperature of the coffee is 76 degrees. I should write. Yeah. And the internal energy of the coffee decreased by 15 kilojoules. The density is that much, the volume is that much, and the specific heat capacity is that much. Calculate the temperature of the coffee. I'm just going to go ahead and write down all the terms that I have. This is the initial temperature. I'm going to say it's T1. Okay. And the internal energy of the coffee is 15 kilojoules, or decreased by 15 kilojoules, which is my change in energy. Unfortunately, it's in kilojoules. I have to remember that when I come back to it. The density is that much, 1.1 times 10 to the 3 kilograms per meters cubed, which I'm happy with. The volume is also in meters cubed, so these two values can be used. Well, if they have to be used together, they can be. So that's density, that's volume. And here we have kilojoules per joules per kilogram per degree Celsius as the specific heat capacity using the symbol C. Calculate the final temperature of the coffee. Use the physics equation sheet. Quite quickly, I can see one equation doesn't satisfy all of those terms. But I will write down the equation that does satisfy this term and that does satisfy this term. The change in energy is equal to mass times specific heat capacity times by the change in temperature. Density is mass over volume. So, of these two things, of these two equations, the statement that or the term that I do not have is mass and change in temperature. I have an initial temperature, remember, but I don't have a change in temperature. So I can't use this first equation right here to calculate change in temperature because I don't have mass, and I can't use this equation to calculate mass because I don't have a change in temperature. So I'm going to use this equation. Density is mass divided by volume. I have density and volume. I could find the mass of the coffee. That's what I'm going to do first. Mass of the coffee is equal to density times by volume. Putting in the numbers that I have, mass is equal to 1.1 times 10 to the 3 times by 1.9 times 10 to the minus 4. I just need to find my calculator from previous questions. Got it? 1.1 times 10 to the 3. You can see that I can put it in exactly like that into the calculator. Times by 1.9 times 10 to the minus 4. This is what I do. Equals, mass is equal to 0.209 kilograms. I'm going to put a green box around it just to remind me. Then I can move on to the next question. Energy change is equal to mass times by specific heat capacity times by change in temperature. The only issue is the energy change is given in kilojoules, and I need that to be in joules. So 15 kilojoules is equal to 15,000 joules. Kilojoules to joules is timesing by 1,000. Next, change in energy. 15,000 equals mass, which is 0.209, and we end up using this term, times by specific heat capacity, which is 4,200, times by change in temperature. Remember, we don't know what the change in temperature is yet. But we can calculate the change in temperature now, and that gives us 15,000 divided by 0.209 times by 4,200. Now, if you want more practice on rearranging equations like this, you have to start off with more basic ones. However, just really quickly, I'm going to put those terms together in the formula, and then I'm going to show you how it rearranges on the side. Watch this. Change in energy is equal to mass times specific heat capacity times by change in temperature. If I want change in temperature on its own, I have to divide this side by mass and divide this side by specific heat capacity. Well, specific heat capacity and mass is being timesed by change in temperature. So let's take those two together. I have to divide this side by m times by c. And if I do divide this side by m times by c, I have to do it on the other side as well. Divide by m times by c. Then what you notice is these terms cancel each other out. Therefore, I end up with change in temperature is equal to change in energy divided by m times by c, which is what we've got here on this equation. this equation that I've got. So now that I've got that, I can calculate the change in temperature, which is 15,000 all divided by 0.209 times by 4,200. The calculator will accept a sum that looks like this, if you can see it. And then it turns out to be 17.0809 degrees. That's my change in temperature. So what does change in temperature mean? Change in temperature means is equal to the final temperature minus the initial temperature. And this, my friends, is the initial temperature. Okay? The change in temperature is the final temperature minus the initial temperature. So, here's where I'm going to have to go back and correct myself, but you'll see what I'm going to do in a minute. 17.09 is equal to final minus 76. Okay. The problem here is the change in temperature isn't 17.09. It's negative 17.09 because the change in energy, it says the energy decreased and the temperature decreases. The decrease in temperature is denoted by negative values, and I should have used negative values throughout, however I didn't, and here's where it might get confusing for some people. Because of that negative change in temperature, this is the equation that I end up with, and solving this equation for T final equals 17 minus 17.09 plus 76 gets you an answer of 58.9. Okay, it gets you an answer of 58.9, which rounds up to 59. Okay, that's my answer.